if you remember last week, we went through this topic, which was the topic of complexity. If you remember, in complexity topic, actually, we discussed different things in terms of Turing machine stuffs. If you remember, we discussed about the Turing machine. We brought an example of Turing machine, and we mentioned the complexity of a machine is measured by the number of moves you need to do to get to halt and accept a string. That would be the complexity of machine. And also, I said if you have easy cases and complex cases, to calculate the complexity of machine, you need to look at the complex cases, not the easy cases only. The easy cases is not the good solution to look at that. And then we went to run example. As you can see from the beginning, that was a string like this. Let's stay in here. That was a string like AB. We wanted to check with this machine to see if this machine accepts this language, this string from a specific language, which is this language or not, a Turing machine. And then we went through all the transitions, all the moves, etc. We went through, and finally we got to the point which was here and said, okay, machine accept this guy, machine accept this guy. And also we checked another example, which was ABA. We wanted to make sure this machine rejects that, and we examined that, and we saw exactly, yes, machine rejects this case. So let's have the chat box in here open in case if there is any question. Okay, so yeah, and then we talk about the complexity of this machine, and we said in terms of complexity, there was somewhere here we could see the presentation in terms of present slideshow. Yeah, in terms of like this guy, it was much easier to understand. And we tried to calculate the complexity of that machine. We said, if you remember, I said the complexity of machine is number of moves you need to take to read specific string, and then say, okay, if it is accepted or if it is rejected. For that specific machine, we calculate different cases. So one case was actually to check if the length of the string is even. I mean, since you want to check if you have something and that thing exactly is repeated at the end. So the half of the string, if it's x, then the whole string is x reverse. So the length of string should be even. So the first part is to check if it is even, the length of string. It takes 2k2 plus 3k plus 2 moves if the length of a string is n and the half of the length of the string is k. So it takes 2k2 plus 3k plus 2 moves. And then the second part takes this number of moves, and then the last part takes something like that. And then if you put all things together, sum up all things together, we will get to n2 plus 5 n over 2 plus 4 is the time complexity of that machine to work on that specific string and say if it is rejected or accepted. For example, if the length of the string is 6, then you see the number of moves you need to do is 6 squared plus 5, 6 over 2 plus 2. But in general, usually we get rid of the rest of the stuff, and also only we consider n2. The running time is proportional to n2, the length of the input string, okay, is squared. So then we talked about the complexity. We said, okay, the complexity of the machine is quadratic in this case because it's proportional to a quadratic statement, kind of. And then we got to this point. We said it's not a good idea to say, okay, if the number of, for example, the complexity of this specific machine is number of moves it needs is like that. For a specific n, you can calculate it. It's better instead to say based on n, which is called big O notation. And we discussed the different categories we will have in the O notation last week. that was the simplest and less complex problems. If it is O1, it is runtime is independent of size of the problem, constant time. Log n occurs when a big problem is solved by transforming it into smaller size by some constant function. It is still not complex. The problems that the time complexity of them are O log n. On is a linear, like the linear search. If you want to find something inside the list, if you have that specific thing inside that list, you need to check all the elements one by one, which is linear. So how many times you check the elements of the list is equal to exactly the length of the list. So that's linear kind of the problems that their complexity is linear. The next a little bit more complex problems are on log n, linear time. They are still okay, and they are not really complex problems. And the next section they are quadratic. They're called quadratic, like the Turing machine we discussed. Still, they are considered as a solvable problem and not complex problem to some extent. And then the craziest type of category of problem in terms of time complexity are O2N. They are exponential runtime to be avoided, characteristic of brute force approach exponential time. One of the example of these cases are breaking a cryptography, a crypto actually. Okay, so actually breaking a cipher or solving a cipher could be exponential time complex. Okay, we got to this point for last week. That was a recap from last week, but now uh, as a general rule, if a problem can be solved in polynomial time on some computers, then the same is true on any other computer. So it's not the matter of to say, okay, it is solvable on this specific problem, but it is not solvable on other problems. No, if a problem is a polynomial time and it is solvable on a computer, then definitely it is solvable everywhere. If you remember from the beginning of the semester, we discussed this course is related in two different topics. First of all, if a problem is solvable or unsolvable, and then if that specific problem that's computable, it's computable, that's computability. And then if it is complex, how complex is solving that problem? If that is computable, solvable, then that's the question of how complex is solving that problem. So the time required to answer an instance of the problem as a function of size of the instance is equivalent to counting the number of steps the Turing machine needs to make an input string representing that instance. What does it mean? It means we say Turing machine are the basis of computing, and we suppose any problem can be dealt with the Turing using the Turing machine. And then, so what is the complexity of problem? Is the complexity of that machine that can solve that problem. And so that's the complexity of Turing machine that can solve that problem. And what is the complexity of Turing machine? The complexity of Turing machine is the number of steps that Turing machine needs to make an input instance representing the instance. Most interesting problems with polynomial solutions are require n2. So we say the polynomial problems are the problems that time complexity is O(n) squared, but it is not just a square. It could be nk. Okay, they are still polynomial, and most of the polynomial time solution are from the type of n2, n3, and 4 rather than n50. We cannot see too many problems of n50 when we talk about polynomial time solution problem. Okay, in the case of problem for which no polynomial time solution are known, the only solution that are typically required are proportional to they are exponential problems. So if you find a problem which is not polynomial or it is non-polynomial time, they are definitely exponential, which are 2 power n or even worse than that. Okay, based on what we talked about in terms of time complexity, we can categorize the whole number of problems in two set of P and NPs. Okay, the set P problem, P is the set of languages L, such that for some Turing machine T deciding L and some K, the time complexity is polynomial. So P are the problems which their time complexity on the Turing machine is polynomial. The complexity of Turing machine that decide languages belong to set P are polynomial. Okay. Well, what is the set of non-polynomial, non-deterministic polynomial. Okay, so to define the set of languages NP, so we have P and NP. Okay, to define the set of languages NP, let's have a look at non-deterministic Turing machine first. If Turing machine is if T is a non-deterministic Turing machine with alphabet sigma such that X belongs to any sigma star, every possible sequence of moves of T on input X T eventually halts. Imagine T is a non-deterministic Turing machine which halts finally. And when we speak out the time complexity of NTM, we assume implicitly that no input string can cause the loop forever. Okay, so we are excluding these things. First of all, we assume machine will halt at some stage. You remember in Turing machine we had definitely the situation that machine can loop forever and it won't halt. Okay, so the machine should halt and there is no input string can cause it to loop forever. Then the time complexity of that non-deterministic Turing machine is the maximum number of moves. We discussed that can possibly make on any input string belonging to it. Then, so that's the definition actually we discussed also. Then what is the set NP? NP is the set of languages that for some NTM Turing machine accepting L, the time complexity is polynomial, where T cannot loop forever, and K is an integer. We say then the language is NP can be accepted in non-deterministic polynomial time. So as you can see, there is not that much differences between P and NP. P is a language uh, which has a time complexity of polynomial. Also, to NP is kind of a language which can be accepted by non-deterministic polynomial time. But that's the matter of another specific things. If you look at the thing, probably we can discuss it here in a better way. So if that's the whole problem, all problems, the big oval, okay, and then we can categorize them into different classes. We have classes of P, we have classes of NP, exponential, and all problems. As you can see, P and NP, all of them are polynomial. They are not exponential, so they still are polynomial problem. What does it mean? It means probably they should be solvable, okay, but that's the matter of how complex is the solution. Is it easy or is it hard to be solved? If it is even very, very complicated and complex, they are exponential, and at some stage they are probably unsolvable. And there are probably other problems more complex than the exponential problems, which sit inside this area into the all problems. But like we discussed in here, we have the P and NP problems. For the P problem, they are easier problem that we can solve them. For the NP problem, still they are polynomial time problem, which they are harder to problem. So in terms of time complexity, you see whatever we get inside toward the P problems, the P set, they are faster to solve. And whenever we go toward the outside of these guys, you can see they are smaller to solve. There's a video which has been shared in here. You can watch it later yourself, but I will share more interesting videos with you later at the class, after the class in the course web page, which are really interesting. So consider problem S such as a problem to solve any incomplete Sudoku grid. S is not solvable in polynomial time, i.e. it takes exponential time for a computer to fill the grid at the worst case. At the same time, given a complicated grid, it is possible to write a polynomial time program, checking if the answer is correct or not. Interestingly, the reason S cannot be solved in polynomial time is due to the fact that there are an exponential number of possible solutions. The above kind of problems are NP problems, a subset of exponential problems. These problems are said to be solvable in non-deterministic polynomial time. They are slower than polynomial time. There is a little bit different in here, non-deterministic polynomial time and deterministic polynomial time, okay? Potentially faster than other exponential polynomial time. Okay, so that's very interesting thing and cases in here. So we say we have the most interestingly for us, we have the NP and P problems. NP is a subset of P problems. P problems, their time complexity are polynomial time complexity. NP are non-deterministic polynomial time complexity. And exponential or exponential time complexity. Okay, they are really complicated and complex problems. Sudoku, jigsaw, they are two examples of the cases, and even chess, they are example of cases which sit in exponential and non polynomial problems. Okay, so what is the main? Let me check if there is any question or no. So what is the main thing actually we can categorize? Let me share with you another screen, the problem we have in here. If you remember in Linux, when we switch to another page, it doesn't show that, so I need to reshare the things. That's not the case. Let me share another string. In here, is that the case? No. Let me exit the full screen. In here. Okay, so let me share a new screen with you. You should be able to see this screen. Okay, can you see the YouTube page I have shared? Can you see the YouTube page? Yes, thank you very much. Okay, so that's a very interesting video. I don't want to play the whole video in here. Probably I will fix on some slides and I'll talk about that. So I will share this video later with you. If you see, so that's a matter of when we talk about the NP problems or P problems, we are talking about these things. Okay, so imagine we have some problems like what is the summation of a and b. They are really easy problems. Okay, they are easy to solve and easy to verify. That's the key criteria of understanding the difference between the P and NP problem. Okay, so P problems are category of problem which they are easy to solve and also they are easy to verify. See, can you understand the difference? Easy to solve and easy to verify. Easy to solve, it is completely clear. Can you solve this problem for me? Yes. How complicated, how complex is it? Is easy. Can you let me know what is the summation of a and b? Yes, I know, and that's easy to solve. And what about the verification? If I have the solution of the problem, can I say if that's correct solution for that problem? That's the verification. Okay, so is it easy to verify that? For the P problem, both things are um, easy: solving the problem and verifying the solution. Okay, for example, if the number is prime, it is easy to solve. Is it easy to say if the number we have said prime is prime? Yes, it is so easy to verify the answer. Okay, so these are the set of P problems. So they are easy to solve and they are easy to verify. But we have another class of problems which they are not usually easy to solve. They maybe see this. They don't say they are not easy. They may be easy or may not be easy to solve, but they are easy to verify, like the jigsaw. If we have a jigsaw and if we ask you if it is possible to solve this problem, to complete this jigsaw, you might say, it's not, I don't know, it's not easy to solve it because that's up to the jigsaw, the size of the jigsaw and the things. Or is it easy to verify if the solution is okay? If someone has completed the jigsaw already for you, can you say, is that a correct solution to that? Yes, exactly. You can check all the pieces one by one to see if they sit correctly beside each other and complete the image we are expecting. So the verification is easy. So they are kind of the NP problem. I think that's the best description of P versus NP problem I have found. I will share this video with you later. You can watch it yourself. So like I said, that would be the case. Exactly as you can see, it tries to say the same thing in here. So for the jigsaw, for example, as you can see, the time complexity is something like that. It is really hard to solve this problem, although nowadays we have computers that solve the problem. When we say the problem is NP or a problem is exponential in terms of time complexity, it doesn't mean necessarily it is unsolvable. No, it means it is hard to solve. We have lots of NP problems which they are not solved yet, but lots of them they have been solved. So that's the matter of how hard it is, the NP. It's not a matter of it is not possible to solve. So as you can see, that's exactly the same case. It is not easy to solve, but it is easy to verify. So that's the matter of comparison. P is a subset of NP. P problems are the problems which are easy to solve, easy to verify. NP problems not easy to solve, but easy to verify. So they are subset of NP. And so that's one of the open problems. There are 7 millionaire problems in physics and mathematics. They are the problems that have not been solved yet, and they have been 7. If you can solve any of them, you will win $1 million prize. So we can start from today to solve one of those problems. One of those problems have been solved already by Riemann, one of the scientists, okay? And still we have 6 problems unsolved. One of those problems, unsolved problems, which scientists are interested to be solved, and the world by itself, let's say, is interested to be solved, is the if P is equal to NP problem. If P is equal to NP problem, what could be the outcome? What would be the outcome? The P problem, in the P problem, you say, is it to solve? Yes. Is it to verify? Yes. For the NP problem, you say, is it to solve? No, it is hard, probably. Is it to verify? Yes. If we say P set and NP set are the same, then what would happen? If you say P and NP set they are the same, what would happen then? Let me see. I don't want to go to settings. Let's just stay in here. If you say P and NP problem are the same, then that means lots of problems which are hard to solve at the moment can be solved easily. It doesn't mean the proving N is equal to NP will give the solution to all those hard problems to us. No, it's not the case. What it means, we can justify that if a problem, if P and NP are the same, if P and NP are the same, then that means a problem which is hard to solve, which is easy to verify, then would be easy to solve. That's all. So one of the crazy NP problem, playing the music. We have lots of musicians in the world, right? So like Mozart, he knew how to compose music to be beautiful. That was a problem. What is the problem? Is it possible to compose music which everyone loves it in the world, or it is very favorite? That's a hard question to ask. That's a hard problem to solve. But what about the verification? Is the music that Mozart composed is beautiful? You can listen to the music and say, yeah, that's beautiful music. So that's one of the NP problems. So if we can verify the P and NP problems are the same, then what does it mean? It means easily we can generate musician like Mozart, right? So that's the interesting part. Okay, so that's the problem of P and NP. Let's back to the presentation. Let's back to the presentation. I will share another screen. Hopefully you should be able my presentation, not the Chrome, not the complexity in here. Share. Okay, so that's the matter of P versus NP problem. Okay, so and reducing one problem to another is the story of how we can reduce an NP problem to a P problem. Polynomial time reduction. So if L1 and L2 are languages over respective alphabets, sigma 1 and sigma 2, a polynomial time reduction from L1 to L2 is a function which for every x belong to sigma star x belong to L1 if and only if fx belong to L2. We discussed that somehow previously. So that's the matter of how we can reduce that polynomial time problem to a simpler problem. Okay, so to say if we can find another languages which is similar to the first language and it is easier, so that's the, we will say L1 is a polynomial time reducible to L2. Definition of, okay, so in NP set, we have NP hard and NP complete languages. Language L is NP hard if L1 less than equal L2 for every L belong to NP. In other words, the problem is NP hard if it is at least as hard as possible, as hard as the problem in the NP. So a problem in NP is called NP hard if it is kind of the hardest problem in the NP set. And NP complete if a problem is NP complete if it is at least as hard as the hardest problem in NP and it is itself also in NP. So that, in other words, the hardest problem inside NP called NP complete. They are the hardest problem inside the N complete. Okay, so that was the matter of complexity. When we talk about the complexity of an algorithm or a problem, so we are talking about two different things. The first thing is the time complexity, which we discussed by far, how much time it takes to solve this problem. That's the time complexity. But we are facing with another version of the complexity, which is space complexity, okay? So far, we have only looked at the complexity of problem in terms of the number of computations required to solve them, computational complexity. We also consider the amount of memory required to compute of computational tasks. For example, what if Homer had a restricted amount of the space in his brain to remember numbers when he tried to add a bunch of numbers together? In the same way, a space-bounded computation involves computation done by a Turing machine using only a restricted number of cells in its tape. So see, we have kind of the space complexity all the time. It was full page. Okay, so the example Turing machine we saw previously that checked the string where XX only uses certain portion of the input tape to decide if this string should be accepted or rejected. We can divide up the space of the input tape into portion visited and not visited. And the time space complexity of Turing machine will be related to the visited portion. Okay, so for Turing machine, you remember the tape was infinite, the length of the tape. You could write and read, you could move right and move left. Okay, that was the definition of Turing machine. So what is the space complexity of a specific problem? Is the portion of the tape actually you visit while you want to accept or reject that specific string. So definitely if it is, so analyzing the space complexity involves seeing how the number of cells on the tape that gets visited at least once relates to the size of the input. For example, for this specific, we saw previously, accept the language. How many cells did this Turing machine need to be able to tell if the string should be accepted? N was the length of the string. So n plus 2 was the number of cells we needed. Why? Because we needed to start from a blank in the beginning and then move to the string. And then we needed to get to the point we see all the symbols of the input string and get to a blank and then reverse back. You remember a lot of forward, backward movement we did to accept this specific string. So the number of cells we need to visit at least once on the tape is n plus 2. So this means that the space needed is O linear. You remember in terms of big O notation, if it is linearly dependent on the size of the input string, it is linear ON. So the space complexity of this Turing machine is then ON. Is the worst case, it is proportional to the length of the input, right? So set PSPACE. PSPACE is a set of all decision problems that can be solved by a Turing machine using polynomial amount of space. That's exactly the same categorization we had for the time complexity. You remember the P and NP. So the set P space is the set which the space complexity is polynomial. Problems in the set P space is the worst case. In the worst case, requires proportional to nk, where n is the size of the input problem. PSPACE complete, a problem is PSPACE complete if it can be solved using amount of memory that is polynomial in the input length, and if every other problem that can be solved in polynomial space can be transformed to it in a polynomial. So that's again the same categorization of the time complexity. The space complexity is kind of the hardest problem in the PSPACE problems, okay? But still it is the same. Okay, so we have finished by far the complexity problem. We have another topic to discuss for the rest of today, which I will share the screen with you. Let me complexity. Let's go in here. No, let's open it. Let me share the new screen with you. Share. Okay, can you see please the new screen, which is the linear bounded automata? Can you see the linear bounded automata? Yeah, very good. Thank you very much. Okay, so the final topic we want to discuss in this course, in this module. So by far, if you remember the Chomsky hierarchy, we started with we had 4 different circles inside each other. The smallest one, the inner one, was the grammar type 3, which was the regular grammar, regular languages, and the machine was the finite state automata, deterministic and non-deterministic. And then we came up one level, the bigger subset, which was grammar type 2. It was the push-down automata. It was context-free languages, and then another bigger one, the 2 bigger one. Actually, if we have the Chomsky hierarchy here, yeah, and we had another bigger one, which was the type 0 languages. It was context-free, and it was Turing machine, if you remember in here. We are going to talk about another set of languages and machines and automatas, which is called linear bounded automata in this module. That's the last topic we want to talk about. So a linear bounded automata is a Turing machine subset. As you remember in here, linear bounded automata is a subset of Turing machine. So it should be possible to be defined in the case of Turing machine. Then. So the first slide, okay. A linear bounded automata, LBA, is a Turing machine whose computations are restricted to the amount of tape on which input is written. So as you can see, it is exactly the same as the Turing machine. We have the tape, but the difference with the Turing machine is that the amount of the tape we can read and write is fixed. It is not like we can move infinitely to the left, we can move infinitely to the right. And we have some symbols, which is starting symbol and ending symbol in here, okay? So that's the definition. We have a finite set of states, a designated initial state as usual, a finite set of instruction as usual, same form as the quadruple of for Turing machine. So we have the same sort of definition of the Turing machine for the instruction. We have initial state, we have a finite set of states, number of finite set of states, everything is the same. So that means we can move right, we can move left, we can write, we can read. They are the same as a Turing machine for LBA, but the input to an LBA is given between the designated end marks. Okay, we have the beginning, starting end marks, and the end marks. Okay, LBA have no instruction which allows it to move past the end mark or erase or replace. So there is no instruction at all. It's not allowed to move toward the left of the end marks and also erase them or replace them with something. So they are there all the time, and you can move exactly in this area, and that's the reason why it is called bounded. Why? But why it is called linear? I hope in the next slide it is available, but I'm curious to mention that. Okay, so the tape head can move only in the portion of the tape originally occupied by W. W is the input string, although an equivalent formulation of LBA sets the limit on usable tape not equal to the length of input rather than a linear. So we say for the LBA, the area of the tape you can use is exactly the same size as the string, as you can see this image in this picture. Okay, but that's not the case. Since it is called linearly, the area that you can talk about is linearly dependent on the length of the string. So if your string is x, the area that you can have could be ax plus b. You remember that's the definition of the linearity, right? So for example, if your string is 3, the length of the string is 3, and a is 2, for example, b is 1, so it could be 2 times 3 plus 1 would be 7. So it is again bounded, but it is 7. It's not exactly the same fixed size as the length of the string, right? So it is allowed then. So the bounded, why? Because we have end marks in here. It is bounded, the area of the tape we can work on. It is linear, why? Because the length of the area that we can use is exactly linearly dependent on the length of the string. It tries to justify what is the difference between the linear and the other shape of functions. You know that, I don't need to go through that. This is the source of the name for this automata. Okay, and like I said, since it is the allowed computation space is bounded by a linear function of the length of the input, LBAs are thus placed between PDAs and TMs, Turing machines. Okay, so as you can see, it is really very similar to the Turing machine in the sense of it can write, it can read, it can move right, left, and so on. And from the other aspect, it is very similar to the other machine. It has final state, uh, finite number of state, and also it has sort of the final state, initial state, instruction, everything. So it is a machine automata that can sit between PDA and Turing machine. LBAs can read and write and move left and right and input tape, but Turing machine have a potentially unlimited amount of tape available for computation. A PDA uses a maximum amount of tape for its push and store, which is also a linear function of length of. Okay, we are trying to compare them here, but PDAs lack the power of LBAs to move left and right. That was the difference. I may ask, what is the difference between PDA and LBA? One of the difference is PDA cannot move left and right, and also it cannot and thus to have access to any portion of the memory encoded to the tape during the computation. So that's the reason why LBA is stronger, more powerful machine that pushed on automata, and Turing is more powerful because you have the whole tape available for you to do anything you want. So you see, for some problems, maybe if you want to check the things, you need to go move to the right, move to the left, forward, backward quite a few times to do something. So if the language you want to work with the machine is really more complicated, Turing machine will give you more capability, more flexibility, more power to do the stuff. So that's the reason why Turing machine is a more powerful machine than the LBA, and it is more powerful than the push-down automata. In push-down automata, we cannot move left, but we have stack, so that kind of facility makes the machine more powerful. And in this case, it is less. It has the less power among all the machines because there is no external memory. It's not possible to write. It's not possible to move left and so on. Okay, the length of machine is limited and so on. So actually we are comparing the Chomsky hierarchy one more time. So LBs come in deterministic and non-deterministic variations defined in a way similar to corresponding type of Turing machine, but it is not known whether they are equivalent. What does it mean? It means, if you remember, for example, in finite state automata, we say if that's a non-deterministic machine, automata that does something, for that we can find a deterministic machine. Or in other words, for any deterministic finite state machine, at least we can find at least one non-deterministic one which are equal, both of them. But that's not the case for LBA. That means, that is, given language L accepted by some non-deterministic LBA, we don't know in general whether there is some deterministic LBA which also accept them. Okay, so this problem has remained open for many years despite the effort for a good many talented and energetic people to solve it. And recall that the context sensitive grammar. You remember, for each specific automata, we had three different parts. We had the automata, we had the grammar, we had the language. Okay. For example, for finite state automata, we had the regular language and regular grammar. Okay. For the push-down automata, we had something similar. For the LBA, we have the same. So it is context sensitive grammar is the grammar related corresponding to linear bounded automata. Is one in which every rule has the property that the right side is at least as long as the left. So do you remember in week number 2, if I'm right? I think so, yes. I think yes. So at that time, if you remember, we tried to define different types of the grammars. At that time, for the context sensitive grammars, we say the right hand side shouldn't be the length of the right hand side in any instruction shouldn't be smaller than the left hand side in particular. Let me see the word in here. So this is not shrinkable then. In particular, rules of the form alpha to empty or epsilon are excluded, so it is kind of shrinkable. You are getting one string or something in the left hand side and you're delivering nothing, so that means you are trying to shrink the input in the machine, so it's not included in context sensitive grammar. And therefore, the empty string cannot be generated as a part of any context sensitive languages except the matter of the empty string, the languages. So why we are talking about that then? So like I said, for any, we have three different pieces, three different parts: the automata, grammar, and language, right? And I said we can make a correspondence between all of them in each level of the Chomsky hierarchy. Well, while you're talking about these things for the LBA, I said LBA is the automata corresponding to context sensitive grammar. But there's a little bit, um, exception in here. What is that? If we are talking about the context sensitive grammar, it cannot generate empty or blank. It is impossible. While the linear bounded automata can do that. So if we want to make a correspondence between them, then except for the matter of the empty string, the language accepted by non-deterministic LBAs or the language generated by CSGs. So it is possible, it could be a good case to ask a question for in the final exam. So in LBA, an LBA could be corresponding to CGS if we exclude the matter of generating the empty. Again, let's read it again. Except for the matter of empty string, the language accepted by non-deterministic LBAs are the languages generated by CSGs. Given a CSG, we can construct a non-deterministic LBM to simulate deriving by G. It says for a specific CSG grammar G, we can have an LBM machine M. M is given an input string W embedded between the end marks, something like that. We can set up a workspace to the right of the input of the length equal to the length of the W, where W insert the start symbol. M then the non-deterministically carries out a derivation from S according to the rules of G, checking after each step to see if the content of the workspace equal W. If so, M halts and accept. It tries to show you how a linear bounded automata can accept or reject the machine. It's very similar to Turing machine, right? You start from a starting symbol in here, and then you work through that, and then at some situation you halt somewhere, and then you accept the string. If there is derivation of W by G, it will be defined by M, and furthermore, it will be defined by some computation which uses no more than the allowed amount of the workspace. Since rules of G are non-shrinking, no line of derivation is shorter than the preceding one. Thus, no derivation of W by G contains a line longer than W, and the derivation can be carried out by M on an amount of tape, which is a linear function, the length of the input, right, in terms of time complexity. The construction in the other direction, simulating the moves of an LBA in reverse by CJ, is similar to that for Turing machine and type 0. However, because of the restriction that rules cannot make a string shorter, a problem arises getting rid of the boundary symbols and the symbols for the state of automation. This can be accomplished by coding sequence of symbol as complex non-terminals. The grammar cannot generate. Okay, that's the whole thing. Actually, I discussed, but I read through the whole thing. Context sensitive and recursive sets. Every language is generated by context sensitive grammar is a recursive set of strings. That is, for every context CS context sensitive languages, there is a Turing machine. Why? Because context sensitive languages and grammars are a subset of a Turing machine in the hierarchy. If you back in here, see these linear bounded automata are a subset of Turing machine. Linear bounded automata can be corresponded, can be related to the context sensitive languages and grammars. That means every context sensitive languages and grammars can be related somehow to the Turing machine because that's a subset of that. Okay, for every context sensitive languages there is a Turing machine which decided it is possible because that's a subset. You know the meaning, the definition of being a subset. If this guy is subset of this guy, then probably using a machine from this category, we can deal with some languages inside this part. But the other way around is not correct. I mean, we cannot find a machine in this category that can work on the languages and a string inside this category. So since linear bounded automata is subset of Turing machine, in other words, since context sensitive grammar is subset of this grammar enumerated languages, so that means we can have a Turing machine that decides any context sensitive languages, and that's the whole correspondence again. Finite state automata, regular languages. What relates these two things together? The grammar, regular grammar. We have the context-free languages, we have the push-down automata, and the context-free grammar correspond these guys together. Linear bounded automata and context-sensitive uh, languages, again, the context-sensitive grammar relates and corresponding them together, and recursively enumerable languages using the corresponding grammar is connected to Turing machine. That was the whole hierarchy of definition.